Okay, so our last speaker before the break will be Huanbo Sun from Max Planck. Take it away.
Okay, thanks. Hello, everyone. My name is Huanbo Sun from the Max Planck Institute for Intelligent Systems in Germany. For today's talk, I would like to introduce a way that can potentially make robots less afraid of contact. We designed a soft, some-sized haptic sensor named the Insight that can deliver useful 3D force information about contact on all sides of the sensor surface. There are many finger-tip-sized haptic sensors available on the market. One of the most commonly used tactile sensor is BioTAC. BioTAC is a multi-module tactile sensor that uses electrical impedance tomography technique to sense contact and can additionally sense temperature and high-frequency vibration. It's somehow relatively expensive to buy and also hard to maintain its functionality in the long-term run, according to our experimental experiences. BioTAC can supply high-speed contact information, but is limited to detect point contacts rather than the surface contact that can tell the contact area or the detailed shape of a contact object or the force distributions. For surface contact detection, most recently, vision-based haptic sensors design have demonstrated a new family of solutions, typically using a high-resolution camera that views the soft contact surface from within. This design strategy can realize compact and high-resolution haptic sensing with low cost, as cameras are nowadays very accessible and computer vision techniques are relatively mature compared to haptic developments. One representative vision-based haptic sensor is GearSight. It has a thin reflective membrane on top of a transparent elastomer layer supported by a flat acrylic plate. Lighting parallel to the surface allows tiny deformations to be detected using photometric stereo techniques. Another representative sensor is called Tactile. It uses a hollow structure with a soft black shell. It detects the deformation of the shell by visually tracking the markers. Other variants using similar techniques are available. As shown here, most of these sensors have relatively flat sensing geometry. Compared to 2D flat sensing geometry, a 3D sensing surface can enable robots to feel all sides of the body parts, like our human skins, like our fingertips or our chest, etc., which let us and the robots work better in messy real-world environments. Thus, we are motivated to design a vision-based haptic sensor that can sense contact on all sides of the contact surface and provide useful haptic information. So here, Insight is our sensor that is a vision-based haptic sensor that uses a camera and a structured lighting system to detect external contact happened on the soft hollow elastomer. The working pipeline is in the following. Insight constantly records images from inside using a camera, feeding these images and reference image under no contact into a trained machine learning model. Makes it possible to estimate the force distribution all over a surface. Each pixel in the force prediction map has 3 values that indicate the force strength in 3 directions. In a force realization on the right, each point corresponding to each pixel in the force prediction shows the force distribution of the contact in both normal and shear directions, even for multiple contacts. There are 4 key design components that make Insight work properly. The soft rigid hybrid mechanical design of the shell, the single camera imaging system, and also the automatic data collection procedure, as well as the deep learning algorithms are used behind the scenes to create a cheap, robust, and easy to use device. Our hybrid structure of a soft elastomer enclosing a stiff metal skeleton ensures high sensitivity and robustness. The soft elastomer is for detecting light contact with high sensitivity, and the metal skeleton is 3D printed and is for holding the elastomer global shape and sustaining high impact force up to 30 Newton for a fingertip. We use an LED ring and collimator to create structural light. The structural light forms a light cone inside the enclosed volume. Each voxel inside this volume has a specific color code with 3D information. Thus, external contact moves the elastomer from one color zone to another. Together with the shading effects, the camera can detect 3D deformation of the surface from a single 2D image. That's how we can encode the 3D information from a single camera view. As shown on the right figure, mimicking our human fingerprint, we also add ridges to the surface to amplify the mechanical deformation and help the system recognize the direction of the surface extension and thus have the ability to tell normal forces and shear forces apart from each other. We designed a 5-degree of freedom test bed to stimulate the sensor in a controlled way with both normal and shear forces over the entire 3D sensing surface. The data is used to train a deep neural network, which is then used at runtime to make the force inference. The sensor can localize the contact with a precision up to 2 millimeters. A force of 100 millimeters is sufficient for reliable detection of even multiple contacts. Notice also how the shear forces are quantified for multiple contacts in this case. The sensor can also track the dynamic contact on the surface with a tiny contact surface and detect the detailed shape of an object. The performance of the sensor is quantitatively evaluated with increased applied force. The position accuracy stays relatively constant, but the force accuracy has a drop, and the force direction accuracy gets better with a higher applied force. The explanation is in the following. These two figures show the influence of the mechanical hybrid structure on the sensing performance. The sensor has relatively stable localization accuracy over the surface. The area near the metal beams has higher force error because contacts near the metal beams don't cause visible deformation seen by the camera and thus have underestimated forces. Compared to other sensors, our Insight has an outstanding performance with the largest 3D sensing surface. Insight has a one-layer mechanical design that ensures robustness. Multi-layer designs by other sensors may have the problem of robustness because the multi-layers may fall apart from each other when constantly under shear forces back and forth. Other parameters like the sensor accuracy is also appealing compared to other reported numbers of the state-of-the-art tactile sensors. In summary, Insight has an overall spatial resolution of sub-millimeters and a force magnetic accuracy of around 30 millinewton and a force direction accuracy of around 5 degrees that can tell normal and shear forces apart. It can sense its self-orientation under no contact when and also detect the detailed shape of an contact object. It has a low cost for the essential components, around $100 US. We have open sourced all the designs and patented the Insight. I'm also pretty happy that several research teams emailed me and then they have already reappeared our sensor in their labs. And thank you very much. And I'm glad to answer any question you might have regarding the current design and suggestions for the future designs.
All right, question back here.
So I have a question. I don't know if I'm audible. Okay, so the test bed that you mentioned, does that provide you ground truth for training the force prediction network?
We have built a test bed. The test bed has 5 degrees of freedom, and then there is a force torque sensor attached to an indenter. The indenter has a geometry of like 4 millimeter spherical dimension, and it makes contacts on the surface and collect data. And then it's around collect data takes us like 2 weeks, and then we train a machine learning model end to end.
Okay, sounds good. Thank you.
So I had a question. I noticed that you made the Insight sensor shaped like a thumb. And I noticed that our thumbs have a non-uniform kind of resolution, right? We have lots of nerve endings at our fingertips and not a lot on our knuckles. Do you think that in robotics, such a non-uniform resolution could be helpful?
Well, take our, this is like a drawback of our sensor design because we have the metal beam to support the structure. A uniform performance overall, the sensor surface is beneficial, but I don't think it's needed. Even like our skin, like our fingers, the fingernail part is not as sensitive as the fingertips. So I'm wondering, I'm also asking myself if this is like the goal to achieve homogeneous sensing capabilities over the entire sensing surface is a good goal. But this is indeed our design drawback. Yeah.
Okay, one last quick question.
So what's the delay of your sensor? Because like for tasks like, for example, dynamic manipulation, you need a very fast, like very quick response from the sensor.
So the current this design, this is the first version of our design. The camera captures the images at 60 frames per second, and then after processing, we get 8 to 10 frames per second of the force map. And we are currently designing a second version. It has it can output 60 frames per second force map.
Okay, let's thank the speaker one more time.